Hey everybody, welcome to another CS302 assignment. For this assignment, we're going to implement this lunar lander game. And since we recently had a successful NASA mission of the Artemis 2 rocket, it makes sense to stay on that theme. Now, the lunar lander, the traditional old school arcade game, the way it worked was you had the space pod that was descending towards the moon's surface. It was free falling basically. And you want to control the rate in which this space pod is downward descending. So if it hits the moon's surface at too fast of a negative or too fast of a downward velocity, then it will crash against the moon's surface, and then the game is over, you lose. And if you're able to successfully land this space pod on the moon's surface, it's a win. So you have an option to use thrusters to essentially modify the rate in which you would descend. And then, of course, you would keep on maintaining the velocity as needed until the space pod lands. So we're going to maintain a list or a priority queue of lunar landers. And the priority is going to be whichever space pod is closest to the moon's surface. We want to have that at the root position because that's the closest to the moon. So we want to make sure that space pod is going to be updated. So we're going to constantly pop a space pod off the priority queue, and we're going to update its thrust amount, which will of course update its distance from the moon's surface and update the velocity as well. And then we put it back into the priority queue. We push it back in, and we constantly keep on just popping always the space pod with the closest distance to the moon's surface, update its thrust, and push it back into the priority queue until eventually all the space pods have either landed and or crashed. That's going to be how we're going to use a priority queue to maintain this. So let's go ahead and just simulate, or to show you, you have a link here you can look at to show you how this arcade game is played. So here's the game in that link in the PDF. This version of the game allows the space pod also change directions and adjust the thrust. You can turn thrusters on with any direction, any orientation of the space pod, which if you do that, you'd have to involve some trigonometry to do this. So I'm going to leave that part out. So our version will be you're just going to be launching, or the thruster only works in upward directions. So the space pod, you can assume, will always be facing upward, never in this direction. Let's go ahead and just simulate this. I'm going to click and use arrow keys here. Let's take a look. So, okay, so in our version, so you can see I'm falling downward, and of course, I'm pushing up on the arrow keys to activate thrusters. And this is going to essentially adjust the rate in which this space pod is falling towards the moon's surface. Now, our version is going to be falling straight down. It won't be falling any type of horizontal direction, but of course, originally you can adjust the orientation of the space pod, but our version will not allow that. And as you use thrusters, you are basically wasting fuel, so you have to also keep that in mind as well. So we can see here we are making our way towards the moon's surface. Very careful, we do not want to crash. So now we're kind of free falling, so you're not using our thrusters at all. I'm really going to burn thrusters right there. And you can see I'm coming towards the surface at a pretty slow rate, so I should be okay. And there we go, landed it. So this is essentially what we're going to be doing. We're going to pretty much just have this lunar lander, and we can adjust the thrusters. And of course, that's going to adjust the vertical speed and so forth. So, and we're not going to really be able to adjust the lunar lander in this direction. We're going to be always having our thrusters, launching us upward at all times. So that's going to be the idea. But we'll have a list of these space pods, and a priority queue will maintain which one we want to update next. And of course, this simulation ends once all the pods land or crashed. Let's go ahead now and just look into this the actual classes we have to implement for this assignment next. Okay, so here's your lander class. So here's a header file provided to you. So we have these private members in our class. So we have a name, the flow rate, that's going to be essentially your thrust amount. So this will be a number between 0 and 1. So 1 will be the max amount of thrust we're applying, and 0 means we have no thrust applied on our lander. The velocity tells us the velocity of the lander at any moment in time. So if it's a positive number, it's sort of moving in the upward direction. If it's negative, it's moving in downward direction. Altitude is its distance from the moon's surface. Fuel amount is how much fuel the lander has. Still landing, a Boolean, so it's true if it's still, I guess you can say airborne, or it didn't land. So if it's true, it's still in the process of landing. If it's false, it's no longer landing, which means either this lander has crashed or it landed successfully. Lander mass is the mass of the lander. Max fuel consumption rate, this is going to tell us how much fuel gets burned for every second. So based on the flow rate and 1 unit of time, this will tell us how much fuel we're going to burn. And the max thrust tells us how powerful, so based on the flow rate, how much I guess oomph, how much force we apply on our lander. So lander has a flow rate and a max thrust, and it will be used to tell us how much strength, how much force will be put on this lander in the upward direction. So the constructor just sets all of these, and I believe I give you this constructor in the lander.cpp file. Now these getters, I sort of give these to you right here because these are kind of no-brainer. And I guess the only difficult functions to write will be these ones, although it's not too complicated. So get status, as given here in the PDF, it returns A if it's still airborne, returns C if it is not airborne. So that means the velocity, so basically it crashed. And an L, it returns L if it landed. So it's crashed if it's no longer airborne. So essentially, if its altitude is 0 or less, and the velocity is less than -2, then you return C, that it crashed. And then if, let's say, the altitude is less than 0, so it's no longer airborne, so still landing is false, and the velocity is greater than -2, then you return L, that it landed. And of course, to change flow rate, I believe I give you that over here. And the simulate function, yeah, it's given to you here in the PDF. So I could read this to you, but it's straightforward right there. Just follow these steps, and that's really it. And then you have to write this less than operator, since we are going to implement a binary min heap. This less than operator essentially is used for the comparisons. Remember when we push back or pop front, we have to bubble up and bubble down. We have to compare between the parent and children sort of priorities. This is going to be our priority. So this will be used to compare the parent with the child sort of priority values, because our PriorityQ class is going to be a template. We're not able to really access the flow rate, altitude, and so forth, because if we do that, then our PriorityQ class is too specific to this type. It's going to be a template. So if we just simply overload this operator, then our PriorityQ class in theory could work for integers, doubles, and even this type, because we have this operator overloaded for our class. And here's how I give you right here. This is essentially how we determine between two lander objects, which one is quote unquote smaller. And these are the hierarchies. And of course we use this if let's say you have a tie. Let's say you have two landers that have the same altitude. Then we look at the fuel, which has a smaller fuel amount, which has smaller mass or larger mass. Sorry. So we just use these to essentially tell us which lander is smaller or has a higher priority, if you will. Okay, let's go ahead and look at the PriorityQ class next. Okay, so here's your PriorityQ class. So let's go through our private members first. So we're going to have this class priority type defined within our PriorityQ class. So every element in our PriorityQ is going to be a priority type, and every element has a key and a priority. So for us, for our main assignment, the key will be a string, and the priority is going to be, in this case, a lander. So T2 will be a lander type. But again, a priority queue, we could have it where T1 could be a string and T2 can be an int, or T2 can be a double. So you want to make this a template class. This is why we want to overload the less than operator for the lander class. So that way we can compare priorities as if we were comparing, let's say if the priorities were integers, and we have to compare when we're doing our bubble up and bubble down, and we have to compare the parent and child's priorities, we of course use a less than operator, right? If, let's say, the priority type, or priority in this case, is integer. But suppose if priority were a lander, we want to still be able to apply less than operator to make the code reusable for any type. That's why we want to use that operator overloaded for the lander class. And of course, we have our two constructors. So these are given to you. And then we have our heap array, size, capacity. So heap array, that's going to be essentially our priority queue. It maintains that binary min heap. It's going to be a tree, but this array emulates that tree. Then the size will tell us how many elements you've used up. And then capacity is going to be how much we're going to allocate to the array. Now remember, index 1 is going to be the root position, and then capacity will tell us how big the array is. So once the size equals capacity, we have to then resize when we do our pushback. So just as a reminder there. And then we have this item, the PQ map. This is used for the update function. So remember, this is used if you want to quickly find something in our map. We don't have to linear search our heap array. So I'll just mention, I'll kind of trace out an example in the video later on to emulate this, but the rest of the class I'd imagine is relatively straightforward from your lectures. So our constructor, this is going to assign the size to be 0, capacity to 5, and it will allocate the heap array to have essentially capacity amount of spots, or amount of elements in this array. Now again, you could set the heap array to be, the length could be capacity plus 1. It's up to you how you do that. Remember, you want to make sure that you are able to determine when the heap array is maxed out for a resize. And remember, size is going to be used to denote the end of your heap array. And then, of course, once size equals capacity, you maxed out, then you have to resize if you push back again. The destructor, I gave it to you. This is very simple. Just deallocate the one-dimensional arrays. You don't have to write that in your implementation file. I give that to you. Pushback, very basic. We pass in a key and priority into this function. This is going to insert to the back of the heap array, and it will call bubble up. Then pop front, a void function will simply remove the front element. Remember how that works. We take the last element, we overwrite the root with it, decrement our size by 1, and then bubble down from index 1. Nothing too shocking. I'll skip past the update for a second and let's go to the rest of these simple ones. So these ones are really one-liners. So get element. This one is basically we pass in a T1, a key, and then we search the heap array and return the value field, or sorry, not the value, the priority field of the object. So this is going to use, it's going to use this item, the PQ map, to find this key. So it's going to find the element with the matching key and return that priority. Again, to get from priority simply returns the root element's priority. Get from key returns the root's keys. These are kind of one-liners. Is empty returns true if you have nothing stored in a priority queue, and it returns false if there's at least one element in your priority queue. Now we also have our bubble up and bubble down functions. Those are essentially the heart of the PriorityQ class. A bubble up, remember, it keeps on computing. You pass in an index into the function, and you bubble up from this index. So when you call this in your pushback function, you pass in the index of that last inserted item. And in bubble up, remember, you keep computing your parent index, compare, and then you swap if needed, and you just keep doing this until you hit the root or until the parent node is less than or equal. Bubble down, remember from class, same idea. We bubble down from an index. Typically, we're going to call this function when we do pop front. We bubble down and pass in 1. We bubble down from index 1 typically. And again, remember, we compute our two children, the left and right child, and then determine the smaller child compared to the parent, swap if needed, and we just keep continuing down the tree until we either hit a leaf or until the parent is less than or equal to both or its only child. So let me go ahead and now just discuss a little bit about this item, the PQ map, and see how it's actually going to be utilized in your program. Okay, so consider the following heap array, and these are going to be our T1 keys. So every element in this array contains a key and a priority. So this priority queue is going to be really a string to an int. So our integers will be our priority types. And notice how if you were to draw this out in the tree form, this would be a valid binary min heap. Now the content right here, that's going to be our items to PQ map. And what this does is going to help us figure out where each element actually is. So for example, if let's say I wanted to update Wario's value from 6 to, let's say, 1. So I have to first find Wario in this array, update the value to be 1, and then bubble up from 5, because if you update Wario's value to 1, then Wario has to bubble up to the root of this tree, obviously. Now, if we don't have this map, we would have to linear search until we finally find Wario, update the value, and then bubble up. That can be a slow process. This map right here, in constant time, will tell us where Wario is. So if I take the map and search for Wario, in constant time, I retrieve Wario, and then this map maps essentially the key to an index. So when I search Wario in constant time, I retrieve the value 5, and then this 5 tells me to go to index 5, and right there's Wario. So in constant time, I can look up records, update, and so forth. Now, the overhead of maintaining this map is really just the following. If we do bubble up and bubble down, if we ever have to swap any elements in our heap array, we have to also swap the respective values in our priority queue. So for example, if I were to search for Wario and in constant time locate Wario and update Wario's value from 6 to 1, we have to then bubble up Wario by first computing Wario's parent index. So 5 divided by 2 is 2. So you have to then bubble Wario up by swapping Luigi and Wario in our heap array, but we have to also swap Wario and Luigi in my map, because now Wario is now going to be at index 2 from now on, and Luigi will be at 5. So you have to make sure our map is consistent around that. Same for bubbling down. If you ever have to swap any elements in a heap array, we have to also swap their indices in our map as well. So that's the whole purpose of this map. So essentially, that sort of goes over our Lander and PriorityQ class. Let's go over some of the main contents, and then of course do an example run through as well. Okay, so before I go into the main you have to write for your assignment, I just want to just show you these two test mains. So this first one, this is just simply just testing out your Lander class. So these are going to be a list of different possible flow rates I'm going to assign to each lander in this very simple simulation. We create two lander objects. So Galactic Giggle and Moondance, I think they're creative names. And of course, our constructor, we assign the various fields, so the weight, the fuel tank amount, max thrust, altitude, all that stuff. So then I just first use the comparison operators to compare which one is, ahead, or which one's closer to the moon's surface, or which one has the smaller value, however you want to call it. And then I run this loop that is basically just constantly applies. So we adjust the two flow rates, and then we run the simulate function, which this is going to just simulate one unit So in this case, 1 second it will simulate. So given the new flow rate, that's going to be the thrust, and it's going to apply that thrust. So it's going to adjust the velocity, it will adjust the fuel amount, and then this will just output the lander info, which I wrote that function over here for you. Just outputs all the contents. And then we just constantly just keep comparing which one's ahead. And we do this a total of, looks like 10 times, or sorry, no, 9 times, less than 9. So 9 times we do this. And we simply just adjust. So we essentially pass, for every second, we just pass in the following. So for example, for L1, we have this first flow rate. For L2, we have that flow rate. The next iteration of the loop, we assign 0.4 to the flow rate, 0 for L2, and so forth. So to compile this, because I have the implementation header file separated with templates, and I use a custom type here and there, it's going to be a little bit of a pain to compile. Well, not really much of a pain, but an extra step. So you have to compile. In this case, it's going to be actually simple, but for the PriorityQ, it'll be a little bit tricky. So here we do g++ lander.cpp, and then lander test.cpp. And then we run it, and that's the output you should be getting. So on CodeGrade, it will just simply test this out. So I have it output to decimal places, but there's no formatting, and CodeGrade's supposed to ignore the white space. At least that's how I always set these up. I'm not sure if it's a new CodeGrade issue, but I had it where I unchecked, so I had it where it would ignore white space. In some cases, it wouldn't ignore, or it's weird, but hopefully there's no problems on this assignment. So anyway, that's the output you should expect to get. I also will test out the PriorityQ class. So here I set a PriorityQ object, Mario Kart string to int. And of course, maybe in this case, these numbers can tell us how close each racer is to the finish line. So we push these records. So Mario, and then 7, Peach 11 pushes into our priority queue, and we update a few elements. So some updates will cause them to bubble up, and some will cause a bubble down to happen. So you have to be able to determine. So I believe for like Wario 3, now Wario looks like maybe he went backwards, I guess. I don't know. But you update Wario by, you have to constant time find Wario using the map, update from 3 to 15, then we have to bubble down. So this may cause bubble down and bubble up. Then Peach, I think, would bubble up because we update Peach's value from the original value, which was 11 to 1. That will cause a bubble up. And then we just basically just pop each element off one by one. So to compile this, here's where it's a little bit weird. We have to do g++ PriorityQ.cpp. Sorry about that. Then we have PriorityQ test. And for some reason, we have to also put lander.cpp as well. And the reason why is because in our PriorityQ class, since we have our header implementation file separated, we have to essentially define our PriorityQ objects that we're going to be using. And since we're going to have a string to lander, we have to essentially link the lander class to the PriorityQ class as well, which is very weird implementation. But I mean, a better way would be just to have everything in one header file by itself. But I kind of want to separate these out so then it's easier for in CodeGrade, you know, it just makes it easier, I suppose, or separates everything, I guess, is the answer. Anyway, so that's how we compile this. ./a.out runs it. And then, of course, that's the output you should be expecting to get. So in this race, Peach is in first place, Mario had second place, Bowser is so far in third place. So we can see whenever we pop it, we output the root element, we output the first place racer, we pop Peach off, then Mario would be at the root. So we output Mario next, that would be the second place in our race. And if we pop the next smallest, then of course Bowser would be the new first place, and so forth. So anyway, that's just gonna test out your PriorityQ class. It's gonna test out the bubble up, bubble downs. Also test out the update element functions as well. So at least we have these two tests. Let's go ahead now go over the main file for the lunar lander, the list of lunar lander objects. Okay, let's go ahead and write or look at the main for the lunar lander simulation. Now, I want to first retract an earlier statement in this video, so I don't want to go back and edit it now, but we're not going to actually simulate this lunar lander by constantly popping the smallest element off and updating it. We're going to essentially simulate by constantly updating any possible lander in our priority queue. And I'll go over the details in this simulation right here. So the first thing you want to do in our main is you want to be able to read in this file landerinput.txt. Now you don't have to actually read that file name into your program. You can actually hard code this and pass this string literally into a file stream open function and then populate your priority queue. Let me show you what's in this file. So we have, I'm going to display here on terminal. There we are. So each line contains one lander object, and in this PDF file it tells you essentially what each content of each line contains. So we're going to have a priority queue object, a string lander. So string will be your key and lander will be your priority type. And here's why we want to use the less than operator, because to compare two landers, we don't know what the priority type could possibly be. It could be an object, could be integer. So you want our class template to work with any possible priority type, which is why, once again, we want to implement that less than operator for our priority queue or for our lander class. So we have to one by one read each of these and push back each one by one into our priority queue. Pretty simple. Now, to run this, let me just go ahead and first compile this program. So we have g++ lander.cpp, then PriorityQ.cpp, then we have main.cpp. Okay, let's run this program. So you can see that we didn't have to read in the file name. You can assume that it's already given to you, or you can hard code this into your program. This will, I guess, make the input a little bit easier, I guess, for simulation. So I guess it makes it simpler. So we're not going to have other input files going to work with. So you can just hard code this into your program. So in this case, you want to output the top three, we want to output the top three in our leaderboard, basically. So what's going to happen is, to do this, we first have to call the get priority get front key function, or priority get front key, to retrieve the record. Then we have to pop it off the priority queue, and then now this lander would now be at the root. This one's now in first place among the remaining landers, so it's really in second place, if you will. And we then call the priority get front key to output the necessary details. And then we're going to pop this. So now Moon Mischief, this would be at the root position. This would be the first place among the remaining landers. So it's really in overall, globally, in third place. And then we output all its content. And after that, we have to push these three back into the priority queue so that we can still work with them. So in our program, in our simulation, we're going to essentially ask the user for lander name and throttle amount. So for example, let me just type in Moon Miss Chief and then 0.1. So this function right here, we have to find Moon Mischief on our priority queue. So you're going to be using update element and get element. We're going to be using these two quite a bit because you have to first find this element in our priority queue. And then we have to update the flow rate to 0.1. Then call the simulate function on that lander. And then we have to update this in our priority queue, which is going to cause a possible bubble up or bubble down. So you have to use get element and update element interchangeably to first update this record's flow rate, call the simulate function after flow rate has been updated, and then we call maybe update element, which will cause this to bubble up or bubble down. Let's see what happens. So Moon Mischief has bubbled up to the root as a result. So now the flow rate was adjusted. So now we have less fuel, and with the moon's gravity, we're actually we're descending at the moment. And of course, I can also do the same thing. I can try to find Astro, and then I'm going to maybe put in 0.01 the flow rate. So you have to find this on our priority queue by calling, you have get element, update element, you have to call it get element to return that value, update it by calling the update flow rate, then call the simulate function, then we have to then update this record in the priority queue, which will then cause a bubble up or bubble down. And the way it's going to work is we essentially, as you can see, we kind of did this in two separate, we first did it for Moon Mischief, then for Astro Whoops. So just to kind of try to believe in this simulation, imagine that this is kind of happening in parallel. So these two racers in parallel, or not racers, landers in parallel, updated their flow rates. So assume that that's what's happening here, just to make it more believable, because it's weird how we had 1 second went by and only this lander updates, the rest didn't update in the priority queue. But imagine that it's happening in parallel, and we're going to be passing in a lot of these until all of them eventually crash or land. So I also provided you, I'm going to go ahead and Control C and end this. I also provide you with a simulation file as well. I think it's called sim01.txt. Let me just, where's ls this really quick. Let's see, where is it? Oh, it is called sim. Okay, so you have cat sim01.txt. So I give you a big file of really all the inputs. You can imagine all the inputs will be valid. Now, yeah, they will all be valid. Actually, there will be a valid valid name for the for an active lander, and the numbers will also be, everything will be valid. So essentially, you can type this in. You can type it in, manually when you're running your code, but this might be a little bit of a pain to do this. So in order to feed this into your program, all you have to do is really just a Linux redirection. So you can just do /a.out, and then just do sim01. So when you're reading your program, reading your input, it's going to read it in from this file. So from your CN, instead of interactively typing the input, it's going to feed this into your CN. And there's the output. So again, another thing to also consider, at any moment when a lander has crashed or landed, we want to output the necessary sort of output. So looks like we have some crashes here. I hope somebody's landed. This is a very depressing. This is it all crash. Something had to have landed, right? Looks like nothing's landing so far. This is a very depressing simulation, but I think other ones will have some landing and some will crash. But anyway, the idea is that we basically read in the amount, we read in the name of a lander and the amount, and then afterwards we simulate that lander, and then we determine if any lander crashed or landed. Then we output the top 3, and then we accept new input. And here it's not going to display the input here because we didn't type it in manually. We kind of redirected the input into this, so it's not going to display the actual input here on the terminal. But essentially what we're doing is reading in a name of a lander, total amount, we perform the updates, and then after we update, we check and see if any lander has landed or crashed. If it has, we display it right there, and then we just output the next 3 in the leaderboard, and we just do this until eventually every single lander has crashed or landed. That's essentially it. So I will provide you with the output file in the along with this PDF, and then all the skeleton files, and those simulation files that I provide will also be used in CodeGrade to test out your lunar lander. So anyway, that's essentially the end of the video. So I hope this gave you some scope on this assignment, and I guess that's it for now. So happy coding, and until next time.